us uses clocks. If it's just for regular timekeeping by using a normal wristwatch, or for navigation using the GPS system, which actually utilizes very precise timekeeping by making use of quantum clocks. For a long time, both theory and experiment have suggested a simple rule of thumb. So if you want a better precision of your clock, you need to burn more entropy. Roughly 1 extra bit of disorder would then correspond to 1 extra unit of energy. So we wanted to answer the question whether this is actually a fundamental rule or if it's simply a limitation of the design of previous clocks.
The model we looked at seemingly had the behavior that you could make it more accurate without having to dissipate any more energy.
For the most clocks, if you pay double the entropy cost, you get double the precision, so you have a linear scaling. However, in our system, this relationship is exponential. So in essence, you pay much less for a certain precision in our clock compared to others.
We could somehow simulate our system and we saw this intriguing behavior, but what we actually wanted to understand is the physics of it. So we wanted to mathematically understand why the system that we found, the model that we found, why this works so well. Yeah, a great thing about this project was that we had expertise on the experimental side from Chalmers with Simone and Simon. We had expertise from Malta on quantum transport, and from our group we also had people with diverse backgrounds, and somehow then we managed to piece these different topics together and eventually understood even analytically why somehow the numerical simulation gave the results they did. I think it's important to even now understand why or how somehow dissipation limits the precision of clocks. Eventually, somehow this limitation might become practically relevant, and it's good to understand already now somehow how to potentially overcome these issues should they arise. But then there's more pragmatic things like information processing and communication. Part of our model could also be interesting and seems to resolve some of the challenges that arise in these fields.
I can think of 3 main direct implications. One would be in the implementation of a so-called autonomous quantum processing unit, which is a completely self-contained quantum processor where you can actually investigate such things as the thermodynamical costs for certain quantum computations. Next, we also have distributed quantum computing, where you have 2 separate quantum computers and you want them to be able to send information between each other. And something you need to realize then is to shape wave packets. Today, that is done in an active manner, but using our tailored coupled spin chains, we can actually do this in a fully passive manner. Then we also have quantum communication, where in many quantum network components in such a system, you actually require very deterministic generation of single microwave photons. And today that is also done in an active manner, but using our type of system, you can generate these photons deterministically in a passive manner.